Tutorial sheet for question 2. Here we've got 8 data signals are sampled and time multiplexed using pulse amplitude modulation. So what we've got here, we're going to have 8 signals. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 signals, and we're going to be using time multiplexing them using pulse amplitude modulation, which in other words means that we're going to be taking a sample of a signal and then rotating that effectively to sample 2, 3, 4, 5, 6, 7 and 8, and taking a sample of the amplitude of that signal as this switch moves between our data signals. The time multiplexed signal is then passed through an ideal low-pass filter. So once we've done that, we then pass that through a low-pass filter. If 6 of the data signals are band limited to 3.3 kHz and the other 2 are 10 kHz, we have to calculate a whole range of things. So let's assume that the first 6 of these all have a signal which has a maximum frequency of f1, and then these final 2 have a signal that has a maximum frequency of f2. So we're told that f1 is equal to 3.3 kHz and f2 is equal to 10 kHz. So part A says, what is the maximum sampling frequency if all channels are to be sampled equally? So using Nyquist's theorem says that we need a sampling frequency which is greater than or equal to twice the maximum message frequency in a particular signal. So if we look at our signals, the highest frequency one, which is 10 kHz, is going to require a sampling frequency which is twice that, which is 20 kHz. Now, as A asks for us to sample them all signals equally, that means that we're going to have an overall, so each signal is now going to have to be sampled at a rate of 20 kHz. So this switch is going to have to obviously be sampling in between that 20 kHz. So for instance, channel 1 is going to have a sample, then that switch is going to rotate around and then have to sample it again, and it has to do that at a rate of 20 kHz. So the total sampling rate, Fs total, is going to be equal to 2 times 10 times the number of channels, which is 8. Of course, that's equal to 160 kHz. So that's our total sampling rate that we need, and that's the minimum that we're going to need if each of these is going to be sampled at an equal rate. So that's part A. Part B says, for this sampling rate, what is the minimum bandwidth of the low-pass filter? Well, if we consider the frequency spectrum, and when we're sampling signals, what we're going to have is something that, let's say we have our signal which we know is 10 kHz, so it's going to have a maximum frequency of 10 kHz, but we've got 8 of those, so we've got 80 kHz that our signal is going to be sat in. So it's going to look something like that, where this is 80 kHz. Our switching frequency, which is at 160 kHz, is going to have something that looks like that on top of it, because we're Nyquist, the proof of Nyquist shows that when you sample a signal like this, the frequency spectrum looks like a convolution of the bandwidth of this signal just repeated at the switching frequency apart. So when we have a low-pass filter, we need to get rid of all this, and of course they're going to repeat over and over again as you go up through the frequency range. So we're going to have a filter which cuts out all of those. So in this case, our ideal low-pass filter has to have a cutoff frequency of 80 kilohertz. And hopefully then, if that's an ideal low-pass filter, that will filter away the frequencies that we're not interested in. Part C says, what would be the minimum bandwidth requirement if the data signals were to be frequency multiplexed using single sideband? So, if we were to look at this as a frequency multiplexing system, now of course we've got 6 signals which each have 3.3 kilohertz. So we're going to have a signal so that would be signal 1, 2, etc., etc., up to signal 6, and each of those is going to be 3.3 kilohertz apart. And then you've got the very wide 10 kilohertz signals from the last 2. So the total bandwidth, if you were to add up all of this, is obviously going to be 3.3 times 6 plus 10 plus 10. And if you work that out, you get 39.8 kilohertz.